Okay, so time to get started. Here's what we were talking about last time. But before we get into the math, let me just remind y'all, don't forget to enter the attendance code for today. Remember, it's on Sakai. It asks, what's the number on the board? Or so, I don't remember my phrasing, but there's the number right there. So as always, it'll be up on the board 5 minutes before class starts. The quiz will be available 5 minutes before class starts, and it'll continue to be available for 5 minutes after class is over. Okay. Right. So, here we are. Talking about linear transformations. Reminder, linearity means this. It means that if you put a linear combination in to the function, then you get the corresponding linear combination out of the function, right? So it's a very natural property to want to have. Of course, minor point, don't forget to confirm that the domain and the target have to be vector spaces. Okay, so let's apply this to an actual example, and we're going to confirm that this is a linear transformation. This is a brute force calculation, but sometimes you got to do brute force. So here's how it works. I'm going to take a linear combination going in, and I'm going to go through all the algebra as necessary. Give me a minute on that, but we're going to show that when you do, you get the same linear combination out. It's a straightforward brute force calculation. Okay, details. This linear combination of vectors x1 and x2. x1 has coordinates. Let's write those out. x2 has coordinates. Let's write those out. Why am I writing out in terms of coordinates? Well, the function's defined in terms of coordinates. And I'm going to need to plug into it, so we need coordinates. Okay. This linear combination, we know how to take linear combinations of vectors. That's just Math 212. Okay. At this point, you got to be a little bit careful, but we're going to plug in this into there and see what comes out. Just make sure to be careful about how you interpret what is x and what is y, etc. This is your x, and therefore goes where the function says the x's go, right? And this is your y, and therefore goes where the function says your y's go. Now, it's just plugging into the function, but anyway, be careful with that. Right. And at this point, it's all shuffling. We just need to shuffle terms around. So the first thing I'm going to do is I'm going to take these terms and shuffle them like this. Now, why would I do that? Well, strategically, I kind of know where this needs to go. I'm going to need to get all the A's and all the X1s kind of over on the left. And I'm going to need to get all the B's and the X2s kind of over on the right. So, let's go ahead and do that with the terms, right? So these terms here need to come over to this side. And these terms here need to come over to this side. So nothing happened there. It's just algebra. Having done that, we separate this as a sum of two vectors. Factor out the common factor of A in all of these terms. Factor out the common factor of B in all of these terms. Right? It's just algebra, not really doing anything. And having not done that, notice that is exactly t of x1. This is exactly t of x2, and we win. So it's just algebra, shuffling things around, interpreting appropriately. Like I say, a brute force calculation. Yeah.
Do we have to, mention that R2 is the vector space?
Yeah, you're right. I should have. That's right. So this is the kind of thing that, typically is sufficiently obvious that it's not, would I have counted off an exam for something? Probably not, right? But if you want to be strict about it, we need to observe that the domain and the target are both vector spaces. Yeah. Yep, good catch. Okay. This is a class in linear algebra. We're talking here about linear transformations. Hopefully no surprise, a lot of the functions that we're going to see in this course will be linear transformations. But while empirically a lot of the functions we're going to see are going to be linear transformations, we can't assume that the functions we see in this course will be linear transformations. So just as a for example, notice that here's a function that isn't, right? Not a very scary looking function, but it's just flat not a linear transformation. The way we confirm it is right here. If this were a linear transformation, clearly these two things would need to equal to each other, right? Factoring out the two, scalar multiplier on the inside, scalar multiplier on the outside, right? We know that's part of linearity. And easy computations, these two things are not equal, and therefore this is not a linear transformation. Okay. Quick observation to make. Some students look at this and think, oh, so you can arbitrate linearity by example. How come we did all this algebra with variables over here? And be careful with this. It's not symmetric, right? So keep in mind what linearity says. Linearity says that a certain condition always works. To show that something always works, you've got to make a general argument. To show that something does not always work, right, is not the same as showing that something always fails, right? So to show that something does not always work, you just need to find a counterexample. And so proving something is a linear transformation is kind of harder in general, and proving something is not a linear transformation tends to be kind of easier because, well, just find any counterexample. So keep that in mind. Okay. All right. So now I'm going to show you a bunch more linear transformations. I think it's just nice to see, hands-on what a bunch of them look like. I'm going to show you a bunch of proofs of things that are linear transformations. I'm also going to leave as exercises for you to prove that some of these things are linear transformations. So here we go. Okay, first, this function here, the differentiation function, I'm going to represent with capital D. Side note, we're going to be doing a lot with this function. This is not just an arbitrary example. We're going to do tons of things with D. So look out for it in the future. What D does is it takes a function in this domain, namely a differentiable function. Flashback to section 2.2. This is the vector space of all differentiable functions defined on the interval from A to B. And what D does is take its derivative, thus resulting in some function. So I claim that this D is linear. This is a linear transformation. The domain, vector space, target vector space, previously observed. So all we need to do is observe, directly confirm that D, the action of D, is linear. So here we go. It's actually a pretty straightforward argument. Not that much to it. Here's D. Right, I'm just going to brute force confirm that if I put a linear combination in, I get the resulting corresponding linear combination out. That's all. I've been straight up, plug and chug, check, plug into the definition. Okay, three-step process. First step in the process. This is just what D is. Right? This is D means take a derivative, right? That's what this says. Nothing to it. Next fact, how do I get from there to there? This is actually old calculus. So early on in a single variable calculus class, Calc 1 class, they write down a bunch of, properties of differentiation. Right after you write the definition of a derivative, they'll write down properties of differentiation. And it's a bunch of boring stuff. The derivative of a sum is the sum of the derivatives. And very quickly, in a Calc 1 class, you kind of get the hang of how you apply shortcut rules, and you just kind of instinctively take derivatives one term at a time. Because, well, that's just how you do it, right? But what you're doing is you're just implementing a property that got written down and kind of underappreciated and then taken for granted. Right? So anyway, it is in fact old single variable calculus that takes us from this step to this step. The derivative of a sum is the sum of the individual derivatives, and with inside of those, the derivative of a scalar times a function is that scalar times the derivative of that function. So here I'm just using 2 steps that are plain old, good old Calc 1 properties. Okay. Right, and then last step, we noticed that, that's exactly the definition of D of F1, and this is exactly the definition of D of F2. So there we go. Proof done. Linear combination in, linear combination out. We have ourselves a linear transformation. Let me pause here for questions. Anybody have any questions? Okay. Let me point out a common misunderstanding. A lot of students get confused on this. A lot of students think, wait a minute, you're telling me that derivatives, right? You're telling me derivatives are linear. But wait a minute. No, they aren't. If I take a derivative of sine x, I get cosine x, right? And surely cosine x is not linear. So what gives, right? What's going on here? How is it that we've proved that derivative is linear, even though clearly it isn't? So what we have here is a misinterpretation, right? This is just a sort of a sloppiness of terminology. Let me draw out the focus again. This is our linear transformation, D. That's our linear transformation. This is the thing which, if you look at its inputs, right, its inputs come from there. If you take linear combinations of its inputs are functions, right? Linear combinations of its inputs gives linear combinations of its outputs. That's what we're talking about. We are not saying that the output itself is linear, right? This function here, this f prime, that's a function from R1 to R1. Right? That's a Calc 1 style function. Not saying f prime is linear. I'm saying D is linear. Let me say that a little bit differently. I'm not saying the derivative is linear. I'm saying that the act of differentiation is linear. Okay, so make sure not to conflate. There's a bunch of different functions running around here with different domains and targets, and you got to make sure to distinguish the one from the other. Okay. All righty. Okay, next example. Y'all remember these functions. Right, this is way back in chapter 1. We talked about how if you give me a matrix, I can interpret that matrix as a function. We did some neat things with this in relation to determinants. We drew some geometric conclusions about determinants from this construction, and then kind of didn't do much with it for a long time. Here we are again. So it turns out this is a linear transformation. And in fact, this is a very important kind of linear transformation. There's a very large category of linear transformations that can all be written in this one special form. We'll get to that later. So I'm going to leave it to y'all to prove this one, that this is a linear transformation. I'm going to refer you, though, to the fact that really you're going to be kind of ripping off this argument here. Right? So you're going to put a linear combination of inputs and then confirm that you get a linear combination of outputs. Structurally, same argument. Now, there's going to be some differences. Here, we use Calc 1. Previous knowledge from Calc 1 about how differentiation works. Right? In this question, you're not going to use any differentiation, but in this question, you're going to be using previously established knowledge about how matrix multiplication works. All right, so we're going to go all the way back to chapter 1 and remember that we know certain facts. There's a scalar associativity and there's a sort of a distributivity and facts that we already know about matrix algebra to finish this proof. Okay, so this is a really good practice problem. I hope you will write that down. Be careful about how you write that down. In other words, the writing down of it is kind of the challenge. Okay. Next one. Actually, there's kind of two in a row here that we're going to talk about. Start with this. This is a weird function I'm going to introduce, sort of an operator. This thing I'm calling S. Claim is a linear transformation. This is a linear transformation that acts on, as I'm defining it here, C infinity functions, infinitely differentiable functions. And the way, given such a function, the way that you compute the output value, and this output value is an element of R1, in other words, a real number. Given a green input, the way I compute the real number output is that formula. Right? Whatever your function is, just do an integral of it from A to B. So that's what S does. And I claim that S is a linear transformation. I'm going to leave this one as an exercise to you. However, beforehand, I'm going to do this harder one, slightly harder one that's right below it, number 4 here. I'll write this one out in full. As I'm writing out this one down here in full, I want you to be thinking in terms of how are you going to copy morally kind of the same sort of strategy to prove this one on your own, on a clean sheet of paper without copying, of course, up here. Okay. Alrighty, so let's get down here to this one. I claim that this thing I'm calling SG is a linear transformation. Okay, now let me explain what SG is. First, let me observe the G. This G has to be given. This is some function. Here's how it's going to play a role in a couple seconds. Right, it's going to sit over there. Whatever this G is defines S by way of this formula. Okay. So, what this SG does is if you give me a function f from C infinity, that goes there. The value of SG, the real number value of SG is then computed by this formula. And I claim that this function SG is a linear transformation. Here's the proof. Now, it's going to structurally, same proof as we've done before. We're going to look at a linear combination of inputs, confirm that we get the appropriate linear combination of outputs. What's that going to look like in this case? I'm going to need to zoom in for space reasons. Bear with me a moment. What this is going to look like is I'm going to look at SG of C1F1 plus C2F2, and I'm going to confirm direct calculation that this is C1 SG of F1 plus C2 SG of F2. Right, there's that linear combination in, linear combination out. This is what I need to show. I just got to fill in now for the yada 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 in the middle. But that's our goal here, and here we go. It's a matter of doing it. Here we go. We have integral from A to B of C1 F1 plus C2 F2 of x times g of x dx. Now, before we go on, let me recognize that is the formula. Right? All I've done here is take this formula and plug it in. Right? Integral function times g of x dx. Here you go. Integral function times g of x dx. Yeah? Everybody good so far? Okay. Now, it's just a matter of doing the appropriate algebra. Okay. First thing I've got to do, how do I evaluate this linear combination of functions, right? If I'm going to compute this integral, I'm going to need to know how to evaluate that function. How do you evaluate a linear combination of functions? Flashback to chapter 2. We defined vector spaces, right? And what does it mean to take a linear combination of functions? Well, the answer was, the way we evaluate a linear combination of functions was, here, let me clean up the, C1 f1 of x, c2 f2 of x. That's how you evaluate a linear combination of functions. You just take the appropriate linear combination of the individual values. Definition. Okay. Times g of x dx. Okay, next step. A little bit of algebra. Just algebra, but let's multiply out that linear combination times g. No tricky curves here. This is c1 f1 of x times g of x plus c2 f2 of x times g of x. Right? Just multiply. Nothing happened there. Okay. Now a little bit of calculus. Recall that if you have an integral of a sum, that is the sum of two separate integrals. Further recall, for each one of those, you can factor out constants. Right? And so, just a little bit of calculus, no big deal. I can rewrite all of this as C1 integral f1 of x g of x dx plus C2 integral f2 of x g of x dx. Just a little bit of calculus. And it's basically all over at this point. Let's recognize that is exactly SG of F1, and this is exactly SG of F2. So, as required, we have confirmed a certain amount of tedium involved there, right? A little bit annoying, but linear combination in, linear combination out. Everybody good? So several things to keep track of in this argument. The big thing, sort of the new, the chapter 5 part of what we're doing here is understanding what linearity means about this function SG. Interpreting correctly, what is SG? What is it a function of? And what should linearity mean given what its domain is, and what kind of things go into this function, namely linear combination of input functions, and then corresponding linear combination of output values. Everything else in this question, most of the sort of the writing at the details, most of the ink on the page comes from just properly treating things that we've previously understood. So this is chapter 2. Right? This next thing here, that's high school algebra. This right here is high school calculus, or a single variable calculus. And whenever you did, it doesn't matter. Right? So, not really that much happens for the rest of the question. It's mostly a matter of just doing interpretation. So, pause for that. Is everybody happy with this argument? Does anyone have any questions about this argument? Okay, this is what you're going to find is the case for, very often when you're trying to prove that something is a linear transformation, interpret carefully what that ought to mean, and everything else is just details to, just take a deep breath and plow through and be careful. Okay. All right. So, moving along, this is called it's called a lot of things. I'm going to call this the Dirac distribution. This is sometimes called the Dirac delta function, but it's also sometimes sort of misunderstood in that sense. But that's a long, fascinating conversation we don't have time for. But anyway, I claim that this thing here is a linear transformation. Here's how it works. This thing here, this delta naught, if you give me a function, smooth, whatever, it doesn't matter, then the value, the real number value of delta naught at that function is computed per that formula. And this is a really easy formula. The way you compute this is just plug in x equals 0. That's what that says. Whatever f is, just plug in x equals 0. That's the value that the Dirac distribution gives for that function. So I claim this is a linear transformation. It's really easy to show that this is a linear transformation. Again, interpret correctly. What kind of, in what sense is delta a function? What's it a function of? Interpret linear combination of those inputs appropriately. And then just write it all down and observe that as we want it to, it does exactly what it should. Okay, good exercise. Please take the time to confirm that this is a linear transformation. And here's a variation of that. This is a linear transformation as well. So notice that this involves taking several derivatives first, after which you then plug in a different value, not 0. And it turns out none of that matters. This is a linear transformation also. Okay. Last one. We've actually already done this last one. In Chapter 4, one of the first things that we did is we looked at differential equations that look like this. And we observed that we can interpret the entire left side as being what you get by applying a certain operator that we called L to some function y. That was the very first thing that we did, was rewrite the left side as L of y. And then the very next thing that we did is we showed that this L had a property that at the time I sort of vaguely referred to as linearity, because frustratingly I couldn't say the word linear transformation yet because, well, we haven't defined linear transformation yet, but I wanted to say linear transformation. Anyway, we have already showed that this function L has that linearity property, and so now we can say it's a linear transformation. So flip back in the notes. Notice that again, first page of the lecture notes on Chapter 4 shows that this is a linear transformation. Okay. Alrighty. Okay. So bad news. I apologize for this, but there's a bunch of little minor bits of junk that have to get said here, and today's the day where we're going to say a lot of those things. So there's going to be a sort of a bunch of miscellany that comes up next. This is not one of those days where we have a nice arc of beginning, middle, end. This is going to be small topic, small topic, small topic, small topic, and there's something kind of tedious about that, and I apologize. It's the nature of the beast. So anyway, here we go. There's a theorem. This is a nice theorem. This is actually kind of a shocking theorem. Is there a question? No? Okay. So, shocking theorem, if you have a linear transformation from V to W, and if you have in the domain, if you have a basis for that domain. So it's important that it be a basis. And then if you tell me the images, if you tell me, and keep in mind images means outputs, right? So if you tell me the images of those basis vectors living inside of W, you wouldn't think that'd be a lot of information. Before I get to the punchline, let me just remind you what's going on here. I guess I need this here. When we say a basis for the domain, the domain itself is infinite, right? There's a vector space. There's infinitely many vectors there. Think R3, right? There's infinitely many vectors in R3. A basis consists of just a couple vectors. Three in this case. So what I'm saying is, pick a basis. That handful of vectors. Tell me what the function does just to that basis. And what this theorem says, and it's a kind of a jaw dropper, but it says that, oh, okay, well then I can then tell you every other value of the function in the entire domain. Right? You give me the value of the function at, let's say, 3 input vectors. I will give you the remaining infinitely many values of the function. So it's kind of shocking, right? Nevertheless, let me prove it for you. It's actually not that big of a deal. Here's this is the entire proof right here. Keep in mind we've got a basis. And if you have a basis, don't forget what that means is that any vector in the vector space can, of course, be written as a linear combination of those basis vectors. Now, this is an old Chapter 2 fact. One of the first things that we did when we wrote down the definition of a basis. In fact, beyond that, we made a definition of what these coefficients are. These coefficients we defined as being the coordinates of that vector with respect to that basis. Flashback. Okay, so having done that, let me observe that whatever vector that is, just writing it as that linear combination, right? Taking advantage of the fact that we have a linear transformation. T is given to be linear. Linear means that you can, when you have a linear combination in, you can write that as a linear combination out. So all I did in this step here is apply linearity. And amazingly, we're actually done. We are done as follows. We were given, in the statement of the question, right, the images of a basis. So these T of V1 through T of Vk, those are given. Whatever vector V we have, I can find these corresponding coefficients. These are coordinates. Y'all remember how to compute coefficients, right? That's just this little algorithm from Chapter 2. So I can compute those coefficients. And therefore, like I say, we're done. I can compute T of V for any vector. There's the formula. I mean, it's mysteriously easy, right? You give me an image of a basis, and then any other vector you give me, I can compute the value of the linear transformation by just following this process. Compute the coordinates, take that corresponding linear combination of the given images, and done. Almost seems too good to be true. So there's different points of view you can take on this theorem, and what does this mean? Here's the way I like to think about it. I like to think about this as illustrating how extremely strong the linearity condition is. Linearity condition is crazy powerful. It's so powerful that if you know you've got a linear transformation, then you only need to know a couple of additional pieces of information. I just need to know a couple of other values of the function, and we're done here. I know everything, right? So that's how powerful the linearity condition is. There you go. Just a for example, get our hands dirty. Here's a linear transformation. Let's call it T here. And notice I've got a basis for the domain. 1, 1, and 1, 2. It's an exercise. Y'all can persuade yourselves that's a basis for R2. Notice that I am giving the image of each of those basis vectors. And with only that information, I claim that we can now write down everything about this linear transformation T. Everything. You give me any vector, I don't care. I can compute T at your vector just from knowing this very, very scant little bit of information. For example, let's suppose that we're going to want to compute it at 3, 4. What's T of 3, 4? Well, 3, 4 is a linear combination of those basis vectors. I've got these coefficients 2 and 1. Right? Linearity. says this, linear combination in, linear combination out. These images were given, and plug and chug, there's the value of t. T is that. You can do this for any vector. I mean, the details will be different, right? Maybe instead of 3, 4, suppose you have 10, 13. Then you're just going to you're going to get different coefficients. You probably have to solve a little system of equations to find those coefficients. You'll have different coefficients in yellow, but you'll still invoke linearity. You can still take a linear combination with different coefficients, but you'll just be taking a different linear combination of your given basis vector images. And again, out comes your answer. So this all works. Like I say, it's really pretty shocking, yeah.
Sorry, how did you do your coefficients again?
It's a little system of equations. In this case, I eyeballed it, right? But in general, if you have some weird vector, 17, negative 42 or something like that, well, then you write a system of equations and you solve for those coefficients. Yeah. Right. So, weird fact. Powerful fact. In the sense that if you want to understand a linear transformation, you only need to know very little information. You just need to know the images of a basis. That's it. Okay. All right. More stuff that we need to do. I need to define a thing. New concept. I need to define something called the kernel of a linear transformation. Oh, yeah. Mm-hmm. Yep. Sure. Well, so these two vectors, oh, come on, stylus. These two vectors are a basis for the domain. Yeah. Did I answer your question? I'm not sure.
Yeah, and those are like two images.
Well, these are two basis vectors, and so importantly, given that so this is the first basis vector and this is the second basis vector for R2, then their images, knowing these images is what allows us to compute the linear transformation. Yeah. Anybody else? Yep.
Do they have to be a basis, or can you write the linear combination of the other things?
They have to be a basis. You need them to span. Well, most importantly, you need them to span the domain. If they span the domain, you can make an analogous argument. Of course, keep in mind if you have a collection of vectors that spans a vector space, then we have a theorem that says a subset is a basis. So so in effect, yes, they have to be a basis. Yep. Yes.
Would you say that in the scope of this course, we would be given bases, or would we have to check to make sure they are bases?
I'm going to say no comment. I don't like to narrow my exam question freedom. Yeah. Sometimes you can look at a vector space and it's reasonable to expect that you can come up with a basis. Sometimes I'll have a specific basis in mind that maybe I'll give you, right? There's a lot of different ways that I might come up with a question related to this. Yeah. Yep. Okay. Right. So moving along, let's talk about the kernel of a linear transformation. Here we go. The kernel. By the way, I hope you all have seen set builder notation before. If you haven't, it's just you read off of it. Pretty much exactly what's written. So, for example, the kernel of a linear transformation is the set of vectors in the domain for which, or such that, the image of that vector is 0. Right? So it's exactly what it says it is. To say it a little bit more sort of quickly, it's the collection of vectors in the domain that land on 0 as the output. Okay. Claim we've actually seen this construction before, some special cases of it. Let me remind you, for this category of function, right? If you've got a matrix, you reinterpret as a function. Well, the kernel is the set where t is equal to 0, so that means that we could reinterpret in this case that we're looking at the set of vectors for which ax equals 0. That's the null space. Or, in chapter 1 language, that's the set of homogeneous solutions for that matrix. Right? So, a couple of different previous points of view. We've made the observation in the past that homogeneous solutions are the same as the null space. This is an old connection. But here we're saying, another way to think about it is the kernel of the linear transformation defined by that matrix. Yeah. By the way, a lot of students will look at this and think, okay, well, we already had this concept of null space. Why do we need a whole new word, kernel, if we already had null space? The distinction is that null space as a construction is constrained to just talking about matrices. So you can talk about the null space of a matrix. The kernel is a more general idea that applies to any linear transformation. Okay. Right. Okay, so explicit example. Just get our hands dirty. Here is a linear transformation. I claim that this projects vectors to the xy plane, vertical projection, like this. Easy algebra to see why that is. This formula, I can just rewrite it as t of x, y, z equals, and now let's just multiply that out. And we get x, y, 0. And notice then, you can see it right here in the formula, all t does is it replaces z with 0. We just lose the z coordinate, replace it with 0. So, smush, right? Vertical smush, squish, projection, whatever you want to call it. Okay, so let's talk about kernel as it applies to this linear transformation. Kernel is the set of vectors in the domain that land on the 0 vector, aka the origin. Right? So in this process, now just think geometrically, what vectors are they that when you squish vertically, they squish onto the origin? And I think it's a pretty easy appeal that it's the z-axis that is that kernel. Yeah? Everybody happy? Okay. Here's another place where we saw kernel. In effect, we didn't say it that way, of course, but remember, previously, we've talked about this L, the left-hand side of the differential equations, if you will, and we have studied homogeneous differential equations. Well, if you're looking for the set of solutions to that homogeneous differential equation, if you're looking for the set of all solutions there, well, you're looking for the kernel, right? So, like I say, we didn't say it that way at the time. We talked at the time about how we're looking for a set of solutions to a differential equation. That's kind of analysis talk. Here we see we can talk about the exact same concept in a kind of a linear algebra point of view. We're looking for the kernel of that linear differential operator. It's linear algebra point of view on the same thing. Okay, next little miscellaneous item that we need to talk about. I got to define image of a linear transformation. Now, good news, we already know what an image is, right? Image is the set of actual outputs from a function. That's all I'm writing down here. I kind of don't even really know why we're writing this down again. I guess because the book does. But the image of a linear transformation, again, set builder notation reads very straight off of here. It's the set of vectors in the target for which that vector is the output value of the function for some vector that actually is in the domain. Right? Again, it just reads straight off. It's exactly what you think it is. It's the set of actual outputs from the function. Okay. And let's apply that now again to this old function that we now know is a linear transformation. A quick reminder, you all are going to prove, right, that this is a linear transformation. Okay. So let's talk about the image of this linear transformation. Reminder, if it's a matrix, I can talk about its column vectors. Another reminder, if you want to if you want to compute this linear transformation, if you want to multiply some vector by a matrix, the way you multiply a vector times a matrix is you're taking a linear combination of those column vectors. Right? That's just there's various different points of view on matrix multiplication. I claim, I've said it a million times, I'll say it a million more. A great point of view on matrix multiplication is to think about it as linear combinations of column vectors. So with this in mind, let's talk about the image, and it's pretty straightforward argument. The image is the set of all possible outputs from this linear transformation. Okay, it's the set of all results from multiplying by the matrix. Let me say that a little bit differently. It's the set of all linear combinations of the column vectors. It's the span of the column vectors. It's the column space. So that's kind of a weird connection. You know, we didn't necessarily see that coming, perhaps. So if you are looking at a matrix as a linear transformation in the usual way, the image of that linear transformation is the column space of that matrix. What I like about this example is that it kind of closes the loop. We've studied column space in task. Right? We've talked about how to find a basis for the column space and certain facts about the dimension of the column space, blah, blah, blah. What we never really did talk about is why we would care about the column space. Right? And if you think about it, it's a pretty natural question. You've got a matrix, and I say, let's look at those column vectors. Let's think about their span. And the natural question is why? So what? This seems weird. Why are we doing this? What does this got to do with anything? How is this natural in any way at all? Right? Well, here's a great answer. The column space is natural because it's the image. That's a natural construction. It's the image of the function that you get by interpreting the matrix as a function. And again, this is a natural construction as well. Right? So very naturally, the column space is a natural object related to a natural interpretation of a matrix. So, cool. Okay. You can see that explicitly, by the way, in this old previous example that we did. I remind you, we're talking about projections into the XY plane. Right? So that's what this matrix does. The projection into the XY plane, you can see the image really easily. There's the image. Right? If what comes out if you take R3 and if you smush R3 down into the XY plane, you get the XY plane. Right? And notice the XY plane is the span of that vector and that vector, and that vector, which is the zero vector, which is pretty boring. It doesn't contribute to the span. But anyway, there we are. The span, the image is clearly the span of the column vectors. Okay. All right. Okay, exercise for y'all to work out. Prove that the kernel is a subspace. Prove that the image is a subspace. Let me refine these for you. The kernel, keep in mind the kernel lives in the domain. The image, keep in mind, lives in the target. Right? So when I say the kernel is a subspace, well, I mean it's a subspace of the domain. When I say the image is a subspace, well, it's a subspace of the target. A couple of real quick comments. I know we're almost out of time here, but don't forget how to prove that you've got a subspace. Closed under addition, closed under scalar multiplication, right? It's very straightforward. Second little observation I want to make for you. We've seen that kernels, at least if you're talking about matrices, kernels are homogeneous solutions. Back in chapter 2, we proved already that homogeneous solutions are subspaces. So when you're going to try to prove that kernels are subspaces, well, this is a little bit more of a general statement, but it's going to look, structurally and cosmetically, the way the algebra plays out is going to look an awful lot like the proof that is in the notes for showing that homogeneous solutions are a subspace. Likewise, images, proving that that's a subspace. Well, images, at least for the case of matrices, it's the column space, which, now let me connect that. That's a span. And there was a suggested exercise. I didn't write it in the notes, but there's a suggested exercise back in Chapter 2. I think it's on the same page as the homogeneous solution thing. That spans are always subspaces. So first, do that old suggested exercise, prove that a span of any collection of vectors is a subspace, and then when you get around to trying to prove that an image is a subspace, it's going to look an awful lot like that span argument. Okay, y'all have a good Wednesday. See y'all later.